Okay, so we are very excited again to have Matias telling us about a unifying framework for the ν-Tamari lattice and principal order ideals in Young's lattice.
Thank you very much. You hear me all right? Hold on, I can't see. I lost the chat.
Yes.
Okay, cool. Thank you. Awesome. So thanks for that introduction. And I would like to begin by pointing out that this is joint work with Rafael Gonzalez de Leon, Francisco Mayorga Cetina, and my advisor, Martha Yip. And so indeed, you might be wondering what, based on the title of this, what this is doing in the room with all the polytope talks. But I will explain that shortly. And maybe I'll actually tell you now the kind of big picture of this talk. So we're going to talk about two different lattices, lattice structures, and they're going to be living together inside this house that's flow polytope. So polytopes, and particularly flow polytopes, will play a big role today. But let's start kind of taking this title apart. So we'll actually start by this Greek letter nu here and there. So that's actually the Greek letter nu instead of the letter V, just to be clear. And of course, the choice of the Greek letter nu is so that I can say that I have lots of new results. But okay, in all seriousness though, nu is going to refer to a path, a lattice path today. So we start with at some point in the plane, let's do the origin and then take some northeast steps and end up at some other point in the in the plane. And that's going to be a lattice path nu. And for a lattice path nu, we can define nu dict paths, which are paths that stay weakly above this chosen path nu. So here's a nu dict path on the right. And for dict paths or nu dict paths, we define a valley to be a consecutive east-north pair, and then a peak to be a consecutive northeast pair. And this is for reasons that are obvious if you tilt your head 45 degrees to the left. And dict paths you probably have heard of before. So they are the special case where nu is the staircase path. So if nu is the staircase path, all the paths that are weakly above that are the classical dict paths. And then furthermore, the nu Catalan numbers, we can define those to be just the number of nu dict paths, just as the classical case counts is given by the classical Catalan numbers. Okay. And so moving on, sorry, I had to get something off the screen here quickly. This set of nu dict paths, we can give them this lattice structure very easily. They inherit the lattice structure from Young's lattice. So this is the lattice of integer partitions ordered by inclusion of Young diagrams. So here's Young's lattice, and we can get immediately a lattice structure on these nu dict paths by just starting with the path nu here, looking at that. And if you notice, there's a region above the path nu that looks like a partition. Well, that corresponds to this partition over here in Young's lattice. And so we take the principal order ideal generated by that, and that gives us a lattice structure on the set of nu dict paths. So that's a very nice, easy lattice structure on these paths. And the cover relation is given by one path being obtained from another by replacing a northeast with an east-north. So basically taking a valley and pushing it up to be a peak, and then that's the cover relation here. So that's one nice lattice structure on nu dict paths, but there's another one, and that one is going to require this notion of horizontal distance, which I'll explain. So the horizontal distance at a point, say R here, is the number of east steps we can take, 1, 2, before we cross into this shaded region here, before we cross nu. And so in this case, the horizontal distance is 2 at that point R. For this other point P below it, however, it's 0 because we can't take a single step without crossing nu. We would end up in this shaded region. And with this horizontal distance notion, we can define a rotation on nudist paths. And that's done as follows. So we'll do this by example. We start with a valley point P, and then we look at its horizontal distance. So we found that to be 0 already. And we travel along the path to the next point, which has the same horizontal distance. In this case, it turns out to be the very end last point here. And we record that, and that's our point Q. And that's going to define this subpath between P and Q. And we're going to take the E step before this point P and rotate it with the subpath between P and Q. So what we do there is take that E step, move it to the end, and shift everything in between one step to the left. And so that's a rotation on these nudist paths. And with this rotation definition, that induces a cover relation where one path is obtained, it covers another one if it's obtained from the other one by a rotation. And that cover relation then induces by the transitive closure of that cover relation, we get the ν-Tamari lattice. And this was introduced by Préville, Rattel, and Viennot recently. And here we see the classical case on the left. So we obtain the classical Tamari lattice for the classical from the classical dict paths. And then for some more general nudist paths, we obtain this different structure. And for any path nu, you obtain some ν-Tamari lattice like this. And so now we have two lattice structures on nudist paths. And now let's talk about the house that they live in. And so they live in a certain flow polytope. But I suppose I should tell you what flow polytopes are first. So a flow graph is a graph that looks like this, for example, on n vertices and edges directed from smaller to larger vertices. And then on this kind of a graph, we can define a flow of size 1 to be a tuple with as many entries as there are edges in the graph. And that's a tuple of non-negative real numbers that so that flow is preserved. And so this first set of equations here is actually telling us that the incoming flow into this graph is size 1. And then whatever flows in has to flow out at the end. So this has to also be of size 1 flowing out. And then flow is preserved. That's what the second set of equations is telling us. And so at any internal vertex 3, for example, here, whatever flows in has to flow out. You can't have any flow getting stuck in the graph somewhere. So that is a flow of size 1 if we have a tuple of non-negative real numbers that satisfy these properties. And if we collect all of the tuples of size 1 and think of that as a geometric object in R to the number of edges in the graph, that is a polytope, and it's the flow polytope for this graph. And polytopes have been nicely already discussed, and for nice description of them, I refer you to Derek Hanley's previous talk for more information about them. But also vertices for these flow polytopes are nicely characterized by routes in this graph. So here, for example, is a route. So if all of the flow goes through that route, then that corresponds to a vertex in this flow polytope. And flow polytopes have a nice triangulation, so we can break it down into simplices using this following theorem by Danilov, Karzanov, and Korshevoy from 2012. And we'll work through this theorem by an example. So we start out with a graph G, and we add this notion of a framing on a graph. So we make it a framed graph. And all that means is we just assign some linear order on at some vertex for every incoming edge and every outgoing edge. So let's just assign the natural ordering 1, 2 to both of these coming in and out. And so with this ordering of incoming and outgoing edges, we can think about whether two routes cross at this vertex here too. And if they don't cross, then they're coherent at that vertex. And then we can collect all of the paths, all of the routes that are coherent under some framing. So if we use this framing that I drew here, 1, 2, 1, 2, then here's a collection of paths that are all coherent under this framing. Because there's no mutually crossing paths here. So that's one maximal collection, and here's another maximal collection. And in particular, they differ at this pair right here, because those two would be crossing. So what this theorem is telling us is that the flow polytope over this graph with this framing, we can triangulate it by collecting the routes corresponding to these maximal sets of coherent routes, which we call a clique. So for a maximal clique, we obtain a simplex in the flow polytope. And so from what we've gathered here, these two collections of maximal coherent sets of routes, we get two simplices in this flow polytope. And yeah, so this is a nice way to combinatorially triangulate these flow polytopes. So let's look at the flow polytope of interest today. So that's going to be called the nu-Caracol flow polytope. And based on some lattice path nu, we can construct it as follows. So we begin with a path graph from vertices 1 to 8, 8 being a plus 3, so this y coordinate plus 3. And then we add some arcs on the bottom here from every vertex to the sync vertex except for the first one. And then here is where the path affects the graph. So if we record the e steps at every run of e steps here, so here's 2, here's 1, here's 0, then 3 and 1, and record those in this vector, then we add the same amount according to that vector. We add the same amount of arcs from the source to the internal vertices here. So we got 2 edges coming from 1 to 3, corresponding to this first front of 2 e steps, then 1, and then this one's missing 1 because this is 0, and then there's 3 and 1, and so on. And this graph is really pretty, and it's called the nu-Caracol graph because caracol is the Spanish word for snail, and these look like snail shells. And so the flow polytope over this graph is the nu-Caracol flow polytope. And these have been studied before by Mechoros and Morales in 2019, and they determined that its volume, normalized volume, is given by this determinantal formula here, which actually counts the number of nu-Dick paths. So where our work comes in is knowing that these are, this can be subdivided into nu-Catalan many simplices. We want to study the triangulation structure of that, of the triangulation structures on this flow polytope. So that brings us to our first theorem, is that if we use the planar framing, which I'll explain what that is, we draw this graph in its planar drawing, and we just order the incoming edges from top to bottom according to this planar drawing. So that's our planar framing at every single vertex. If we do this framing, then the triangulation that we get has the dual graph given by the corresponding principal order ideal in Young's lattice generated by the path nu that we use to construct this nu-Caracol graph. And so that's result 1. But then if we use a different framing, the length framing, which is also very easy to explain, it's just order these arcs by their length. And so here at vertex 4, 1, 2, 3, 1, 2. And if we have multi-edges, we just pick one of them to be longer. In this case, the one that's drawn on top is the longer one. So using the same path again, but now using the length framing, the dual structure of the triangulation is the ν-Tamari lattice. So that's really the main result, that these two lattice structures live in the same flow polytope, and that we just triangulate it using 2 different framings. But I should point out here that we didn't actually use Prebill, Rattel, and Viano's description of this using nu-Dick paths. We used a different description given by Ceballos, Padrol, and Sarmiento in 2019 using IJ trees instead. So I did want to point that out, that the proof actually uses this different nu-Catalan object. And just some final remarks here. So in the classical case where nu is the staircase shape or the staircase partition, the Tamari lattice and the corresponding principal ideal in Young's lattice have appeared together as dual structures before in the Pitman-Stanley polytope, but they appeared as dual graphs of subdivisions, not triangulations. And they also were constructed in very different ways. So what our work does is not only considers the general case for any nu, but also unifies them under the umbrella of DKK triangulations of a particular flow polytope. And I should also mention that results by Mecheros, Morales, and Stryker also extend these triangulations. Because these graphs are planar graphs, these results also extend to certain order polytopes as well. And if you know something about H-star polynomials or H vectors, I just wanted to point out that the H vector for this new Caracol flow polytope is given by the new Narayana numbers. And so that's something interesting as well. But that's all I wanted to say today. So hopefully that leaves a little room for questions. So thank you.
Thank you, Matias, for a very excellent talk. Let's react or clap on camera. Are there any questions from the audience?
I think I have one.
Sure.
So like, there are all these like bijections between like Catalan numbers and like dig paths and like other things like triangulations of a polygon or something. Is there like a new version of that? Like what's the new triangulation of a polygon?
Yeah, that's a really good
or
question.
Other stuff, I don't know.
Yeah, so that was kind of what was brushed under the rug here using these diagrams here. So these IJ trees are what these diagrams are called that index the new Tamari lattice here. And so you can, if you were to fold these, this endpoint here and this endpoint here, kind of fold them around together, it would look like a triangulation of some sort of n-gon. And so it is related, and but it's somewhat generalized. So I think you can kind of think of them as like triangulations, but then you color some of the edges as like multiple colors. I think that's one way to think about it.
Thank you.
Mm-hmm.
I have another question. So in the change of ordering that you were given to the incoming edges, the difference between one and the other is that you flip the ones that were drawn below, right? And
exactly, yeah.
Okay. And both give you unimodal triangulations of the.
Right. So if we use one framing, the planar one, we get the principal order ideals of Young's lattice. And if we flip the bottom arcs to be also on the top, according to order by length, then we get new Tamari lattice as the dual structure of that flow polytope, the triangulation of that flow polytope. And there might be more. If we do some different, manipulation of the two, who knows what we would get? We could get lots of fun things.
Okay, that was very cool.
The answer to this may be no. I don't. Is there any relationship between this Caracol business and non-crossing arc diagrams? I feel like there should be, but like I can't figure out what it should be.
Probably. So you can index the simplices by any Catalan object. So I know non-crossing partitions and so if your thing is a Catalan object, it probably has a new generalization, and then you can index these simplices using those, I'm sure.
Yeah. This is cool. Thank you for a good talk.
Thank you.
Are there any other questions? Okay, if not, let's take a second to thank both of our speakers again for wonderful talks. This was a really nice session.